In the Netherlands, a construction crane calamity.
I heard metal to metal. It was definitely shocking.
A potentially fatal flaw strikes an iconic San Francisco bridge.
If any one structural component fails, the entire bridge can go down.
In Louisiana, mystery as a massive whirlpool drains a lake.
It's the site of one of the greatest engineering catastrophes in this country.
And tragedy strikes a Florida beachside condo.
I was coming out and saw the condominium physically collapse right in front of me.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. One basic rule of construction is to check and double-check your math. Because when engineers miscalculate, the results can be catastrophic. Like this bridge project in the Netherlands that nearly crippled a town.
With this job, small mistakes led to a major catastrophe.
As a complex crane operation went drastically wrong.
I was, of course, very fearful. It was difficult to understand what did I see.
Every engineering student should look closely at this case. What went wrong here could so easily have been avoided.
The low-lying Netherlands are home to 6,000 miles of rivers and canals, forming the densest network of inland waterways in Europe. The town of Alphen aan den Rijn lies at its heart. As local journalist Vera Vergunst explains.
The waterways here in Holland are very important to connect the whole country. So this one is the only one you can go from north to south, and it's used by cargo ships, sailing boats, pleasure boats, and the biggest yachts.
With so many waterways, bridges are a way of life.
So this bridge, the Queen Juliana Bridge, is the most important bridge in Alphen because it connects that side of the city to the other side, and it's the only bridge in the center you can pass by car.
It's not just about city traffic. Without this bridge, cargo and large pleasure boats wouldn't be able to take the scenic shortcut that this river offers.
About 20 times a day, traffic grinds to a halt as the Queen Juliana Bridge opens to allow larger vessels to pass through town. Back in 2010, the constant use had taken its toll on the steel, and the decision was made to replace the lifting span.
Now, this meant entire sections of the bridge would need to be lifted by crane and carried to the riverbank. The challenge was how to get the cranes close enough to the bridge.
With the banks cluttered with businesses and homes, engineers decided the best option was to work from the water. Amateur photographer and drone operator Dick Van Smieren filmed the project from his canal-side balcony.
It was very spectacular to see in this area the pontoons with the big cranes on it. It was high, it was impressive.
The plan involved two massive cranes, one 700 tons, the other 400 tons, each mounted on a barge. This tandem lift would see the bridge deck lifted from a third barge, and once horizontal, slung between the cranes. The two barges would sail more than 300 feet to fit the bridge onto existing mounts.
I think a lot of people thought it was a pretty crazy idea to put cranes on pontoons, but I think here in Holland the engineers are like very innovative, and we trust them. So we were like, well, this will be okay.
Since I love filming and photographing, I took the drone and it showed, of course, the impressive perspective of the huge cranes and how those cranes were ready to pull the bridge and take it to its new place.
August 3rd, 2015, lifting day. The town looked on as the cranes took the strain.
Actually, that day it looked normal, so impressive to see it.
At first, the crane stood perfectly balanced, almost as if frozen. But once the lift started, the picture changed dramatically.
But the first thing where it really was strange was when I heard metal to metal. You would not expect that in so careful operation. And then you could really see the bridge moving, touching the crane. It was definitely shocking. You see that collapse. Of course you think there are victims. The first thing I did was calling ambulance.
Footage from a security camera reveals just how dangerous the situation was.
Four houses on the water collapsed, and the two other houses on the other side of the street also collapsed because the crane was so big. He destroyed all of the houses, and a lot of other houses were damaged by the accidents.
For the authorities, getting into the houses which the cranes had crashed onto was the priority.
Incredibly, despite 20 people being injured, no one was killed. With cars unable to cross the bridge and river traffic on hold, the authorities raced to get the bridge repaired and to determine exactly what had gone wrong. The town turned to engineering expert Jacques Ertz to analyze the accident. And Jacques turned to Dick's footage.
The drone film from Dick was really useful because it was give a nice overview from all different angles. It really helped to figure out what they were doing on the job site. We started with the data from the lifting plan. After that, we checked condition at site was exactly as what they had planned.
The key problem was in the balance calculations for the delicate and highly complex lift operation.
The preparation, it's quite a lot of engineering to be done, especially in this case with two barges, or actually three barges, and one barge with a load as well. Two cranes, wind, current, maybe even waves. So it's really complex, so you have to do really proper engineering in advance to determine if it's feasible or not.
Major discrepancies between the theory and reality quickly emerged, based on miscalculations of the rig's stability.
Especially on the small barge, there was a lot of additional equipment and material. Also, the ballast condition of the barge was not according to the plan, and all these changes reduces the stability.
The inherent instability of the barge with the smaller crane caused it to list to one side. The excessive sideways forces buckled the crane's mast, which toppled, pulling the bridge deck and the larger crane with it.
They have done some preliminary checks in the beginning of the project, but during the engineering, a lot of Small things have changed. Small errors or changes in the engineering can lead to major accidents.
Leaving the town without its only vehicle crossing wasn't an option. So the authorities planned a second lift operation. This time, nothing could go wrong.
For the second attempt, a bespoke floating crane was used. It's an expensive option, but one which hugely reduced the risk of a disaster.
The bridge was finally operational, nearly a year late, and thousands of dollars over budget. But for residents, the reopening was a huge relief.
The town was, I think, very happy when the bridge was finally reopened, because it was really missing in the city center.
When engineers push boundaries, sometimes the danger comes from the outside. But other times, even the mightiest of structures can be threatened from the inside. Like this construction calamity in California, with an engineering marvel that came dangerously close to catastrophe.
One of America's most iconic bridges could have been one snap away from collapse.
A cutting-edge design that could have turned into an epic engineering disaster.
The design defect could have brought the whole thing crashing down.
San Francisco is home to some of the West Coast's most iconic postcard views.
I love San Francisco. It looks stunning, it has culture, amazing architecture, and of course, an endless, beautiful waterfront. In fact, the city is surrounded on 3 sides by water.
All this water means one thing: bridges. The Golden Gate is the city's most famous bridge. But there's another here that's a far greater feat of engineering: the San Francisco-Oakland Bay Bridge, better known simply as the Bay Bridge. It's the city's most important crossing, as engineer Andrew Framier explains.
The San Francisco-Oakland Bay Bridge by itself is the biggest workhorse of all of the 8 crossings that are in the San Francisco Bay Area. And so on an average day, hundreds of thousands of people commute across that bridge. And it's very important for the community and for the economy for that bridge to stay open and operational.
When it was built in the 1930s, the Bay Bridge was the longest and most expensive bridge in the world. But in 2013, a radical, unique middle section opened. Although just a fraction of the length, it alone was California's most expensive public works project ever. With an iconic single tower topping 500 feet and a span of more than 1,200 feet, this is the longest self-anchored suspension bridge in the world. Bridge engineer Brian Moroney helped build this epic structure.
Here we are at the top of the tower of the self-anchored suspension bridge. If you look to the west, you see the beautiful skyline of San Francisco. And as a bridge engineer, looking at the on and off ramps and the Bay Bridge going in and out of Yerba Buena Island Tunnel, very exciting.
It's not just the view that sets this bridge apart from its peers, but the way that it works. Unlike a conventional suspension bridge, which has 2 cables anchoring it to each side of the crossing, a self-anchored suspension bridge is entirely supported by a single cable. Here it forms an open-ended figure 8, supported by the single 525-foot tower.
One of the most challenging parts of this entire bridge is the cabling system of the self-anchored suspension bridge. The anchorage is on the east end. It comes up the top of the tower, continuously goes around, wraps around, comes back up to the top of the tower, and then comes back to the other side of the east anchorage. The entire length is over a mile, so it's a long cable.
The cable consists of 17,000 individual wires, bundled together and anchored at the Oakland end of the bridge.
We're here at the east end of the self-anchored suspension bridge, deep within, inside the superstructure. This is the splay chamber. This is basically where all of the cables come down and anchor. So the parallel wire strands, each one of them, even though it's approximately about 1 meter diameter main cable up on the bridge, they splay out here in the splay chamber, and you see all these parallel wire strands, and they splay out into smaller groups of wires. They get cast into what we call a socket. Then the socket is screwed into a rod, and the rod goes all the way back against an anchorage. That's a heavily, heavily reinforced steel wall, and it's screwed in tight.
This unique bridge wasn't just built to break records. The radical design is to combat something San Francisco is famous for: earthquakes. Journalist Charles Pillar explains.
We live in one of the most earthquake-prone environments in the world. There's 2 major earthquake faults that are adjacent to the Bay Bridge and affect the Bay Area more generally: the Hayward Fault, which is just in the East Bay Hills, and the San Andreas Fault, which is closer to the coast. Both of these are faults that have had major earthquakes in the past, and in particular, the Hayward Fault is thought to be likely to have a major earthquake possibly quite soon.
In 1989, the San Andreas Fault triggered the massive Loma Prieta earthquake, and a section of the old Bay Bridge slid from its supports. Engineers realized the entire section was vulnerable because it was built on soft mud. So when the new span was built, the solution was to have a single tower standing on the only solid rock in the area.
This self-anchoring method means the cables are attached to the end of the deck rather than the ground, which means the structure has much more flexibility in an earthquake.
The self-anchoring section of the Bay Bridge was built to survive an 8.5 magnitude earthquake, but something significantly smaller almost sent it crashing into the bay. In the 1989 Loma Prieta earthquake, the road deck of San Francisco's Bay Bridge slid from its supports. With the new bridge, to prevent that from happening, the decks are joined to the legs using connections called shear keys. Engineer Brian Maroney explains.
Shear keys are devices that hold on either side of the bearing to keep the superstructure from sliding.
The Bay Bridge shear keys have 2 parts: a 10-foot square base bolted to the eastern pier by 3-inch wide steel rods. This links to a second plate on the road deck above, allowing movement much like a trailer ball hitch. As well as coping with everyday loads, if an earthquake hits, the design allows the 2 parts to shake independently without causing damage. Although engineers didn't know it, long before the bridge was complete, trouble was brewing in these crucial connections.
The shear key rods were concreted in place in 2008, but the giant nuts couldn't be fully tightened until the bridge above was constructed too. This was a massive project, so the bolts sat there untightened for 5 years.
And when the nuts were finally tightened, 32 of the steel anchor rods fractured immediately. This massive fail left the bridge vulnerable.
Had an earthquake hit, the very elements designed to protect it could have led to its ultimate destruction.
Metallurgical engineer Lisa Fulton investigated this potentially catastrophic problem.
This bridge is what is known as a fracture-critical bridge, which means that any one structural component, if one fails, the entire bridge can go down.
Despite the structure's supersize, the failure was caused by a microscopic problem known as hydrogen embrittlement. It's a type of corrosion where hydrogen atoms diffuse into a metal structure. As the atoms slowly recombine into hydrogen molecules, they form a gas that creates pressure inside the metal. Ultimately, the rods become brittle.
Hydrogen enters the steel and has an embrittling effect on the steel. So embrittlement is when something breaks without absorbing a lot of energy.
Even under very little pressure, hydrogen embrittlement can make steel snap. With a massive force, like the shaking of an earthquake, any brittle steel would be a serious risk.
With the discovery that the shear key rods had failed, people were obviously worried that other steel bolts and even the main cables themselves might be at risk.
This bridge is an amazingly unique creature. The question is whether this self-anchored span, this unique design that is replicated at this scale nowhere in the world, whether it can withstand the strongest level of quake that could occur on the Hayward or San Andreas Fault. And Caltrans says yes. We've done our computer modeling and we feel confident of it. Of course, on the other side are many engineers who doubt it, who question it.
If the officials say the bridge is safe, you just have to trust them. But had the main cable been vulnerable, with this type of bridge, it couldn't be replaced. There would have been no choice but to tear the whole thing down and start over.
This is the cable that holds up the suspension span. It's crucial that there not be any corrosion on it.
What was not in doubt was that 32 of the shear key rods had fractured. If a quake hit, no one could be sure what would happen to the other rods, and engineers didn't want to find out. The rods couldn't be replaced, so they worked round the clock on an alternative solution to hold the shear key in place.
What we did is we created a saddle, just like a saddle that you put on the back of a horse, and then we strapped or pulled down, cinched down that steel saddle, and then pre-stressed it and tightened it.
A pair of steel clamps called saddles were fitted over the sides of the shear key, with multiple steel rods and cables holding it in place, effectively strapping the shear key to the bridge leg. Whatever happens to the rods, the shear key isn't going anywhere. Finally, in 2013, the revolutionary new eastern span of the San Francisco-Oakland Bay Bridge opened to traffic. It was 10 years behind schedule and billions of dollars over budget, but San Francisco had added another striking bridge to its collection.
This ended up being the most expensive bridge ever built in America, but it could have been one of their costliest construction catastrophes.
When engineering goes wrong, the cause of the calamity can be huge and obvious for all to see. But sometimes, the simplest mistakes can have devastating consequences. Like this mystery in Louisiana and a massive lake that vanished.
A tiny miscalculation changed the entire landscape forever.
Once this epic engineering fail started, there was no stopping it.
This catastrophe quickly spiraled out of control.
It's the site of one of the greatest engineering catastrophes in this country.
Louisiana, home to the Big Easy and endless bayous, where the mighty Mississippi River meets the ocean.
When I think of Louisiana, I think of swamps and lots of water. There's the long coast beside the Gulf of Mexico. It has vast bayous threading through the Mississippi Delta and endless lakes in between.
For thousands of years, the river has dumped layer upon layer of sediment to create a vast, flat landscape. Geologist Tim Dukes has been studying the ground here for decades.
We're located in what is called the Gulf Coast area, the coastal plain, generally pretty flat.
Although the state is mainly flat, geologists like Tim have found the occasional mound that hints at something precious lurking beneath the surface.
These places are irregularities in that because they're salt domes and topographically higher, significantly higher. There are literally hundreds of these salt domes that are found in Louisiana and thousands that are found in the Gulf Coast. Around the edges of these, there are a lot of areas where drilling for oil and gas can take place, and it's been pretty prolific.
In the 1970s, prospectors were drawn to a salt dome on the western edge of the Mississippi Delta, the so-called Jefferson Island, on the banks of Lake Peigneur. Tim was here in 1980 when engineers were searching for oil.
We're located on the shores of Lake Peigneur. There was a drilling rig that was located out more or less in the center of the lake, and they were drilling supposedly around the edges of this salt dome.
Michael Richards Sr. was working on Jefferson Island at the time.
When I came to work here in 1969, we used to mow grass between here and the pilings. There was a grove of pine trees right here.
On November 20th, 1980, as the rig drilled into the lake bed, the drill jammed solid, and Michael grabbed his film camera.
Soon after the drill bit became stuck, the whole rig started to tilt. The rig workers knew that something was seriously wrong and evacuated the rig. After they reached the shore, it soon became clear they'd had a lucky escape.
The rig quickly disappeared through the lake bed, and a giant whirlpool formed where it had stood just minutes earlier.
Once a whirlpool had formed, the spinning water rapidly eroded a hole in the bottom of the lake. Although small, it was big enough to suck in the whole lake.
Michael continued to film.
We were standing on the porch on the second floor of this house that you see here that's sunk about 30 feet, looking down on the lake and watching the barges rolling around, a tremendous vortex. And then at one time there were 3 different vortices, each one turning and swirling.
The lake was rapidly being sucked underground, but the force of the whirlpool soon started dragging more than just the water with it. In addition to the water, about 65 acres of Jefferson Island also disappeared through the lake bed.
The land in the bottom of the lake was peeling off in great layers like a cake. And behind us, the water was liquefying the soil. And in that direction where there were trees, the trees were holding, the roots of the trees were holding the soil. So the soil slipped and the trees laid down. You can still see the tops of some of those trees today.
Michael discovered that filming on location could prove deadly.
Sheriff's Department came in and told us it's time to go. So we left. And not long after that, the house and all this land slipped in. The progress started moving in this direction.
With Lake Peigneur no longer a lake and a huge part of Jefferson Island missing, everyone was left asking, where on earth had it all gone?
Jefferson Island was the surface evidence of a salt dome, which is why rig workers were looking for oil trapped beneath the salt. But as they knew all along, there was also a massive salt mine being excavated beneath the island. In fact, it was about the size of a skyscraper.
The salt mine was at considerable depth, several hundreds of feet. I think the deepest level was down to 900 feet, and it was an active mine at the time. They were pulling out salt. This is an example of what they were after.
It turns out that instead of discovering oil, the rig had inadvertently drilled through the roof of the salt mine.
Because of the safety conditions that were present and the procedures that they had established, all of the miners were able to get out without anybody being injured or killed.
This explains where all the water had gone, but not why the rig had drilled into the salt mine in the first place. After all, it had been known about for 60 years.
When deciding where to drill, the engineers used a method called triangulation. Basically, angles from 2 or more fixed points are used to locate another point. The problem was they made a mistake in their calculations and drilled in the wrong place.
This minor miscalculation not only wrecked an oil rig, it also brought a watery end to a fully functioning salt mine. But it was an unexpected new beginning for Lake Peigneur.
The suction created by the whirlpool was so strong, the canal that used to flow from the lake into the Gulf of Mexico reversed, basically refilling Lake Peigneur with seawater.
After a considerable amount of time, the waters came back up, all the barges popped back to the surface, and the lake kind of achieved its present level.
Lake Peigneur is now 20 times deeper, and Jefferson Island is significantly smaller.
All of this land slipped in. It's unbelievable, the magnitude of this catastrophe.
It just goes to show that when it comes to engineering, getting your calculations correct really is essential.
Some engineering fails lurk hidden for years after the construction crews have left the site. But with others, the fail strikes before the job is done. Like this condominium in Florida, and an engineering error with truly tragic consequences.
This real-life disaster was set in motion right from the drawing board.
Saw it actually physically collapse right in front of me, and you just saw a huge, huge ball of dust.
A fatal failure that forced the engineering industry to re-examine the rule book. Florida's seafront city of Cocoa Beach is sandwiched between the Atlantic Ocean and the Banana River. Famed for its long sandy beaches and one of the largest surf shops in the world, this town actually owes its existence to America's space program. Local engineer Julie Keller explains.
Close by to this area, we have the Kennedy Space Center, which brings in a lot of science and engineering people and needs the availability to house them.
In the 1980s, with NASA's shuttle program in full swing, Cocoa Beach was busy building.
There were building booms back in the 80s and the 90s, and anytime you have a building boom, there's always a need for construction to be done faster and at a quicker rate.
In December 1980, to keep up with demand, work started on a new 5-story condo, the Harbor Key. Although it was never completed, it would be built like many other condos across the country.
We are headed to the site where the original Harbor K condo was supposed to be built. This would have been a prime piece of real estate to put a 5-story condo on. What we have here is an example of what the Harbor K could have looked like. So this building is typical of the area. It's a condo that's 5 stories high.
Each level would be made up of large flat slabs held up by columns. To maximize internal space, there would be no additional horizontal beams. The slabs would be strong enough to support themselves.
Concrete is great for construction. It's very strong as a supporting block, but when it's used as a floor or roof panel, it has to be self-supporting. That calls for serious reinforcement.
Setting steel bars inside concrete is the key to structural strength. The concrete resists squeezing or compression, while the steel resists bending or tension. But to work properly, the exact height of the bars is critical. With Harbor Key, the plan was to use a process called reinforcement chair design.
So what we have here is an example of what you would see on a typical construction site where the slab is being poured. and you would have these form boards so it would make the mold of where the concrete's going to go. The location of this bar is critical in the placement of the slab because all the calculations are based off of where this bar is.
The idea with the chair system is to hold the rebar at exactly the right height. If those measurements are out by even a couple of inches or centimeters, the whole thing can come crashing down.
3 months into the project, on March 27, 1981, the construction team was pouring concrete to create the roof 5 stories up. But shortly after 3 p.m., the build went drastically wrong. Kent Fay was 20 at the time, working as a lifeguard just across the street.
On that day, I was leaving work to head over to have my paycheck cashed over at the local bank. And as I was exiting, was coming out and saw the condominium, Harbor K condos that they were building, saw it actually physically collapse right in front of me. And you just saw a huge, huge ball of dust.
The collapse happened so fast, there was no warning for the workers.
I quickly ran over there. I got up on the scene. I was dealing with people that were severely, severely injured. There was a young man on the ground that was actually in shock. They went and got him up and had him help me start attending to people that were injured.
Residents and construction workers rushed to the scene to join the rescue mission, quickly followed by airmen from the nearby Patrick Air Force Base. 23 workers were injured, and despite the rescuers' best efforts, tragically, 11 died. The disaster left the community reeling and demanding answers. March 27, 1981, Florida's Cocoa Beach condo collapsed without warning. Within an hour, a team from OSHA, the Occupational Safety and Health Administration, was on site to investigate.
According to official reports on the accident, investigators found clear evidence in the wreckage of what had gone wrong.
The investigation discovered a number of failures, most notably in the reinforcement chair design. Engineer Julie Keller explains.
The reason that this is critical on this particular condo is that the steel not being in the right location was found to be because these chairs were not the right size. The chairs were not the right size because the engineer signed off on the shop drawings showing the chairs in the incorrect size. And that led to the steel being under so much stress that every time you put another floor on it, there was additional stress on the condo. So it led to a brittle failure.
Brittle failure is when concrete cracks suddenly and without warning. As structural engineer R.N. Silapan demonstrates.
In this test, we are going to be determining the flexural strength, the bending strength of concrete. Right now, we have applied a load of over 5,500 pounds. Now it's way over 6,500. These concrete specimens are expected to break with a bending strength of about 500 or 600 psi. As you can see, this beam was tested to failure. However, this is not how it is in the field. In the field, when we're actually constructing a building, you would have reinforcing steel in there, which greatly enhances its capacity.
But the brittle failure in the concrete wasn't just the result of steel being positioned incorrectly. The original design didn't call for thick enough concrete in the first place.
Even though this bar should have been down here, the slab was designed to be 8 inches thick. So that's what the engineer had done in design. But the American Concrete Institute has a code which says that a flat slab supported on just columns should be 11 inches thick. So the distance between the compression and where this bar should have been, that critical number that was in the calculation, should have actually added 3 inches, not just the inch that was lost due to the chair size.
Typically, in order to increase the bending capacity of beams and slabs, the steel is placed in the lower portion of the cross section. But in Cocoa Beach, it was placed almost at the midpoint, which effectively does not contribute to increasing its bending capacity, because as you can imagine, when this beam bends this way, the bottom is in tension and the top is in compression.
Concrete works really well in compression. It does not work well in tension. A teacher a long time ago told me that if you join your hands together, you can see the example from if you push on your hands, you see your skin wrinkles on top, and that's compression. So you can see that happening, and then you look under your hands and you can see the skin stretching, and that's tension. And that's where the cracking forms, and that's why this needs to be in the correct location in order to do its job.
It seems that there were multiple miscalculations. The chair size was out, the thickness of the concrete was wrong, and the calculations in the original drawings were based on rebar that was 1/3 stronger than the steel used in construction.
The calculations were wrong on every floor, so as each was being completed, the problem was being compounded. It was just getting worse and worse.
Ultimately, these factors combined as the 5th floor was being poured, leading to a failure known as punching shear.
With the rebar set too high, the bottom of the panels were being overstressed. When the concrete fouled, the panels fell, but in effect, it was the support columns punching through the concrete.
This type of failure happens in reinforced concrete slab structures. Where the columns support the slabs, they're subjected to very high forces. In this case, the slabs failed at these crucial points, and with no support, the structure collapsed.
They continued to build, and then when they put the 5th floor on there, it just failed suddenly.
There were mistakes at every stage, but by getting the numbers wrong at the design stage, this project was doomed from the start.
Although it was too late for the workers who lost their lives, the Harbor Key condo collapse led to more rigorous enforcement of engineering and construction codes in Florida and across the United States.
It's critical that engineers learn from tragedies like this to help prevent anything like it from happening again.
When engineering goes wrong, the cause of the calamity can be huge and obvious for all to see. But sometimes, gigantic projects can be threatened by the smallest of flaws. Like this building in Chicago, where a beautiful addition was an ugly catastrophe in the making.
This could have been deadly for people on the streets below.
A layer of heavy marble covering the outside was a lethal disaster waiting to happen.
We're up there on the side of the building. We are shocked at the condition of the marble.
This building was designed to have high impact, just not like this.
The Windy City has long been famous for its bold architecture. With a skyline dominated by massive skyscrapers, the city has been home to the world's tallest building more than once.
For more than 100 years, Chicago and Manhattan have battled each other for the title of the greatest skyline, which usually meant the tallest building.
By the 1970s, thanks to huge leaps in structural engineering, Chicago led the world in skyscraper design. Master stonemason Robert Gerskis spent 3 years working on one of the city's tallest towers.
All right, here we go, ladies and gentlemen.
Although few know the story, Chicago's Aon building has a very dramatic history.
Chicago traffic helicopter 1 by X-ray. This is Toll.
Completed in 1973, this 83-story skyscraper was the Standard Oil Company headquarters, known locally as Big Stan.
Beautiful, beautiful. Very nice.
When built, it was Chicago's tallest building and the 4th tallest in the world.
This is the building right here, formerly known as Standard Oil Building, 137 feet off the hard deck, all the way up to the top. Right now, we're approximately 1,200 feet above ground level, and the views are spectacular. Totally awesome.
Big Stan wasn't just super tall. In engineering terms, it was a trailblazer. As architecture historian Rick Keel explains, it pioneered a new structural system.
The Aeon Tower actually has the frame of the building and support of the building in the outside wall. And the outside wall forms a giant square tube that goes up into the sky.
For decades, most towers were supported by columns spread evenly throughout the building. But for Big Stan, architects placed steel columns in tightly packed rows around the outside, known as a tube frame, with a central core of columns.
That tube is then tied across between the floors to the center elevator core, which gives it more strength.
Tube-framed towers could resist greater lateral forces from high winds or earthquakes than their predecessors, allowing them to grow taller. With Big Stan, the columns were long, slender triangles running the full height of the tower, interspersed with narrow windows. But the architect had bigger plans beyond the revolutionary steel skeleton.
As well as innovating the internal structure, the architects wanted to create an iconic exterior that truly shone in the skyline.
That shine came from one of the most ambitious cosmetic jobs since the Great Pyramid of Giza. All 83 stories of steel would be covered with top-of-the-line Carrara marble from northern Italy. As material scientist Laura Powers explains, marble has a long history in construction when appearance is a priority.
Carrara marble is a wonderful stone. It was Michelangelo's marble of choice for sculpting because it is so pure, it's very predictable when you're working with it. Because it is such a special stone, when someone wants to make a statement, they'll use Carrara marble.
Marble can be highly polished and solid blocks will last centuries. But structurally, Big Stan didn't need any more support, and so the outside was purely aesthetic.
To achieve the designer's intended look, Big Stan took advantage of the latest engineering advances in rock cutting. The plan was to cover the triangular columns with thin sheets of marble, just 1 1/4 inches thick, running from street level to the top, 83 stories above. In all, it took 43,000 panels, each weighing as much as a motorcycle. In 1973, when Big Stan opened its doors for business, it was the tallest marble-covered building in the world. But just a decade later, the shine began to fade. Routine inspections revealed the slick marble coat was cracking and in danger of crashing down to the ground. This is where restoration specialist Robert Gerskis came in. He captured this unique footage as he assessed the damage.
We're up there on the side of the building. We are shocked at the condition of the marble.
The fear was that the sheets of rock, as heavy as 2 men, could have fallen from 80 stories up.
As early as the construction phase, there were reports that the marble was not secure.
It's reported that on Christmas Day in 1973, one of the slabs fell from Big Stan, and it pierced the roof of the neighboring office. The fact that it happened on a public holiday might have been a blessing in disguise.
This is the actual piece from the Aeon buildings. Full panel, typical panel is like 4 foot by 5 foot. This is about 11-pound piece right here. 1,000 feet up in the air, all the way down to the ground. This would do some serious damage.
So, Why was the same type of marble that had lasted over 500 years in Italy struggling after less than 20 in Chicago? It seems thin sheets of marble and the Chicago climate were a bad combination. Structural engineer Michael Scheffler analyzed the damage in the 1980s.
Well, it had proven the test of time in Italy. Italy has a very benign environment. Chicago has a much different climate than Italy. In Chicago in the winter, you can get below zero, and you can get up to 100 degrees. And this had a profound effect on the material's behavior.
The problem was something called thermal hysteresis, which basically means an irreversible bending or bowing out of a panel caused by temperature change.
With the building known as Big Stan exposed to the extremes of Chicago weather, the outside of the panels were repeatedly heated or cooled more dramatically than the inside. This gradually and permanently altered the internal structure of the marble, causing the panels to bow outwards.
They were beginning to warp and pronounced bowing outward as much as 1.5 inches at the center of the panel in a 4-foot 2-inch height.
But thermal hysteresis wasn't just bowing the panels. As they deformed, they became more vulnerable in critical places.
Many of the panels were experiencing cracking and spalling at their connections. It was revealed through testing that the material had lost, in some cases, as much as 90% of its strength.
Not only did it spoil the clean lines, but there was a real risk that the panels could literally pop themselves off the building.
In the 1980s, the marble facade on Chicago's Standard Oil Tower was cracking, and something had to be done to protect people below. A very temporary solution was found until a complete redesign could be put into place. Stone restoration specialist Robert Gerskis explains.
This building was a total challenge because we had to put on straps on over 43,000 pieces of marble. If it wasn't for the straps holding on to marble on the side of the building, we would have a huge problem. Pieces probably would fall off.
The ultimate solution was just as bold as the original design. Robert was one of the master stonemasons tasked with replacing all 43,000 heavy marble panels.
This job was just massive in its undertaking. This is the largest, probably the biggest recladding job, the tallest recladding job in the world at the time.
The audacious plan was to recover the entire building in a much tougher Chicago weatherproof stone, granite.
We started recladding in 1988. We had to take off 43,000 pieces of marble and replace it with 43,000 pieces of granite, all done on the outside, and the building is still occupied. They did not shut down the building. So the people that worked on this building had to be the best of the best in the business.
Replacing the heavy panels, more than 1,000 feet up in high winds, was more than just a technical challenge for Robert and his team.
And sometimes we had to contend with very, very high winds. It was very, very scary. You had to be aware of your surroundings. And with that being said, courage is learning how to manage your fear.
By 1992, after nearly 4 years, the biggest renovation on one of the tallest buildings in the world was finally complete.
Replacing the thousands and thousands of panels is said to have cost $80 million, nearly half the original construction cost. But nearly 30 years later, the cladding is still going strong.
While the drastic solution was expensive, it was a huge success. And since Big Stan's original high-class cladding catastrophe, architects and engineers no longer use Carrara marble for external coverings anywhere in the U.S. With big engineering, overcoming gravity is always a key consideration. But when your very stability is under threat, every calculation is vital. Like this bridge in Canada, which was hit by a disaster that left a nation reeling.
This was the worst industrial accident in Vancouver's history.
An engineering catastrophe with devastating consequences.
Had I been there that day, I wouldn't be here today.
This tragedy left a lasting mark on everyone involved.
If I wake up, I can still see that, even after 62 years.
Vancouver, on Canada's Pacific coast, is a bustling seaport. It was established in 1792 by George Vancouver. Around the natural harbor, he named the Burrard Inlet.
The Burrard Inlet is a shallow fjord carved by ice that separates downtown Vancouver from the Pacific mountain range to the north. It's a sheltered inlet and ideal for shipping.
To keep things moving on and off the water, bridges have long crossed this busy shipping lane.
There have been bridges across this stretch of water since the 1920s, but all have proved problematic.
The main flaw was with the section between the main supports, the central span of the bridge.
The first bridge was hit by several ships. One even got wedged beneath it, ripping away its center span.
Repaired and reopened, the new bridge had a center lift span, which brought problems of its own.
The new span had a lifting mechanism to allow ships through, but became legendary for its traffic delays. In 1 year alone, the central span was raised over 5,000 times.
By the 1950s, it was clear that a completely new bridge was needed. Luc Lessard moved to town to work as a foreman on the new crossing, called the Second Narrows Bridge.
In 1957, I moved from Quebec to Vancouver. The beauty of Vancouver, when I arrived, I was amazed.
The best solution for both increased traffic and larger ships was a cantilever bridge.
A cantilever is effectively a bridge where each span is only anchored or supported at one end, while the other end projects out like a long arm across the water until it meets a section from the other side.
Yet this one was a little different. Many cantilever bridges stand on large supporting piers, with the steelwork pointing skywards. But here, to get maximum height for shipping, this one was effectively flipped upside down, with the road deck running on top.
The new design did away with both the problems of its predecessor. It would be high enough to allow large ships to pass underneath, while traffic could continue to flow on the road above.
At the time, Peter Hall was a young draftsman when he was asked to film the construction.
I didn't own a movie camera, and never having used one before, I borrowed one from one of the fellows in the drawing office.
Building this towering structure was no easy feat. Luke and his team of ironworkers were often doing back-breaking work more than 100 feet in the air, and Peter was right up there with them.
The work of a bridgeman or an iron worker is a very dangerous job because most of the time we work on the air. Any fall, we know that be our life. And those days especially, we did not use a safety net or cable or tie down. We were completely free walking on any piece of the bridge.
Back then, men were walking across steel beams high in the air with no safety nets, no harnesses. This was a seriously dangerous occupation. These workers put their lives on the lines every day.
One of the biggest challenges for the ironworkers was that this type of bridge is unstable during construction.
The benefit of a cantilever bridge is that once complete, it's strong and stable enough to cross a large expanse of water. But the downside is that they're tricky to build.
With this upside-down cantilever, Vancouver's Second Narrows Bridge couldn't support itself until each span was complete. So workers installed temporary structures called falseworks to support the span. Once a span was complete, it was fully self-supporting, and the falsework would be removed.
This was going to be a jewel in the crown for construction in Canada. But then things went very wrong.
As Vancouver's Second Narrows Bridge took shape, on June 17, 1958, Foreman Luc Lessard and his team were lifting a 55-ton section into place. Less than an hour before quitting time, without warning, the span collapsed. "79 workers, including Luc, fell more than 100 feet into the water.
We heard a big noise, so the bridge went down underneath our feet. First thing I remember, I was on the bottom of the ocean, 35 feet below the top of the water. Then I finally saw a light coming up from the sun through the water. I managed to get above the water. My leg and my arm was broken.
Peter Hall was lucky. He'd been called to the office earlier that day.
June the 17th, 1958. Started out like any other day. I was able to see the bridge from the top of the hill. And as I looked at the bridge, it was in the water. When I got there, it was chaos. There was bodies in the water, bodies trapped in the steelwork. I just couldn't film a lot of what I was witnessing. A lot of the people that were being brought off the bridge, I classed as friends.
Despite breaking his arm, leg, and his back, Foreman Luc was one of the lucky ones. 18 of the 79 workers that fell that afternoon perished. In the wake of the tragedy, the official report concluded that there was a design and calculation error in a crucial part of the falsework. It seems the layout of the temporary arm beneath the fifth span of the bridge was fatally flawed.
The steel was bracing the heavy span of the bridge until a new section was fitted. But the exact layout of the falsework wasn't stable enough to support the weight of the incomplete bridge above.
As the new section was being moved into place, the falsework gave way, taking that whole section of the bridge with it. Bridge engineer Daryl Madsen explains further.
The steel had lots of strength, but it lacks stability. There is no set calculation method for falsework short of it has to be big enough to hold the load and it has to be stable.
The heart of the problem was using a row of beams as a base for the falsework.
This is very much like if you take and you stack a whole pile of blocks one on top of the other. There's not really a strong connection between the blocks, and eventually they'll fall over. This is the same thing where we have the bridge sitting on top of a block, which is this column, sitting on top of another block, which is the beams. The problem with this is that there wasn't any stability to that lower block. Like it wasn't even like I have a block that's this big that takes a bit to roll. They're very thin webs that just rolled over and flopped over.
This was the worst industrial accident in Vancouver's history, and one which perhaps could have been avoided with a relatively simple solution.
Had they put bracing in at 4 locations, one on either side, either truss, and one at the support of the foundation and one at the support of the column. Had they put 4 sets of bracing in, that's all it would have taken.
It's easy to say with hindsight, but it seems like a relatively minor adjustment could have prevented a major catastrophe.
The bridge was rebuilt and finally opened in 1960. In 1994, to honor the workers who lost their lives, it was officially renamed the Iron Workers Memorial Second Narrows Crossing.
Often in my mind, at night, I can see what was happening. I can still see that, even after 62 years.
120,000 vehicles drive over the bridge every day, which is both a tragic reminder and a testament to some truly courageous men and all that they've achieved.
With big engineering, the devil is in the details. Numbers are checked and double-checked, but sometimes even the best-laid plans can go awry. Like this precision project in Denmark that took everyone by surprise.
When you're using more than 20 pounds of high explosives, you really hope you've got things right.
In 2018, a landmark demolition blown completely off course.
It stopped, and then it was going the wrong way, and everybody was in shock.
Experts and residents were left wondering what had gone wrong.
It's safe to say this demolition did not go to plan.
Vordingborg in the south of Denmark is an ancient port town and home to some iconic Scandinavian architecture.
The picturesque old ferry town of Vordingborg has buildings that date back to the 14th century. The Danes know how to build things at last.
As the shipping industry grew, so did the port, which was relocated to a new site across from the town's waterfront.
In recent years, the port has undergone massive development. The ambition is for the town to be one of the largest grain exporters in Europe.
The waterfront has long been towered over by a giant silo. The 170-foot-tall structure was built strong to be able to contain the massive weight of hundreds of tons of grain. Like most silos, it was built as a cylinder.
The cylinder distributes forces evenly around the outside, allowing them to withstand much greater pressure than square shapes.
As the new industrial port was being developed, the old harbor, with its standout silo, was also in line for a makeover. Local journalist Kim Eriksson covered the story.
There's a lot of development in Vordingborg area with new bridges and new railroads. The silo hasn't been used for many years. Before it was used for animal feed. Because of development of the area, it was decided to demolish it.
A strong and stable cylinder is ideal for storage, but when the time comes for demolition, they're complicated structures to bring down.
Most buildings are held up by supporting columns that can be blasted away and the whole thing collapses like a concertina. But silos have solid walls with no natural weak points for blasting.
There was an added layer of complication. The silo stood next to the town's cultural center and library. It was critical the tower fell in the right direction. So, like felling a tree, demolition experts chopped a wedge into the side, planning to force the silo to fall away from its neighbors and into a specially prepared landing zone.
Demolition by implosion might seem like the easiest way to knock down a structure, but with such a tall cylinder, the smallest mistake could escalate out of control.
Silos are very strong as complete structures, with the forces all nicely balanced. But like all cylinders, as soon as you remove a piece that disturbs the balance of the entire structure, it becomes unstable and unpredictable.
The blast was so complex, explosive experts spent 6 months preparing. April 9th, 2018, Demolition Day. With cameras rolling, engineers cleared the exclusion zone.
On the day of the demolition, everything seemed to be okay, and there was a big safety area, and there was 2,000 people, I guess, over here and over on the other side of the sea. Everybody was very excited about it.
At 5 o'clock, the explosives were detonated.
When this explosion happened, the silo actually went the right way for a few seconds. And then it stopped, and then it was going the wrong way, and everybody was in shock.
Not only had the silo fallen the wrong way, the force of the impact had crushed the end of the library and cultural center. Thankfully, as firefighter John Hansen discovered, the exclusion zone had kept people safely out of danger.
There was no people at this time in the building. Everyone who worked at the building have gone to home for holidays. It was good luck that nobody was hurt at the time.
The disaster was the talk of the town, and with the cultural center in ruins, residents wanted answers.
With all that planning, it should have fallen neatly into the landing zone, but clearly something went horribly wrong.
So, why was the silo blown so spectacularly off course? Professor of Engineering Per Golterman has a theory to explain the chaos.
What I have here is a model of the Vordingborg silo. We have removed some of the concrete and we are going to blast it. I'll use my blasting finger here. We'll remove that, and this is what was supposed to happen.
The initial blast went as planned, but the precise way the silo started to collapse made the difference between success and failure.
What did happen was that these parts here started to be crushed, and when this uncrushed part hit the ground floor, that's when it started to go all the other way back, because all this concrete here has been destroyed.
Instead of immediately toppling, the silo slumped backwards, and as the top of the wedge hit the reinforced base, the kick made it fall in completely the wrong direction. And while the report into the disaster is still ongoing, Per believes the demolition could have been done differently in the first place.
One thing was, for instance, to take it down in steps. Instead of taking the whole thing in one go, he could have taken it in 2 or 3 goes. But of course, it would probably have cut 3 times as much and taken 3 times as long.
While it might not have been as spectacular, taking the silo down piece by piece was probably the best way to go.
Thankfully, no one was hurt. The cultural center has been repaired, and Vordingborg's dockside has a large, clear area for new development. When you're pushing the boundaries of engineering, catastrophe can hit before the building is even complete. But sometimes, trouble can lie lurking for decades, waiting for the right moment to strike. Like this engineering failure in Northern California, on one of the nation's most hazardous stretches of railroad track.
Cantera was the most disastrous, one of the most costly, and it affected a lot of people.
An epic miscalculation that nearly destroyed an entire ecosystem.
I could see fish floating in the river, belly up, and it was an indication of what had happened.
Almost every living organism along a 40-mile stretch of river was wiped out.
In the late 1800s, railroads became vital to America's prosperity. As the Southern Pacific Network grew across the western states, engineers faced some of the nation's toughest terrain.
The West Coast Railroad has connected Southern California with the Pacific Northwest for about 100 years. The route runs right past one of the tallest volcanic peaks in the US, Mount Shasta. is stunning and a real headache for railroad engineers.
To avoid the mountainous terrain, the railroad was forced down into the Sacramento River Valley. Train historian John Senior worked on the railroad for more than 20 years.
One of the big obstacles for this part of the railroad was getting up and out of the Sacramento River Canyon. The railroad follows the Sacramento River up canyon in basically what's called a water grade on about a 1.7% grade. They got to a point where there wasn't any way to continue following the river. So they got to Cantera and they made a loop. They did a 180-degree curve and started up the canyon wall at the same gradient. The curvature that was there was pretty extreme, and it is for a modern railroad, even today at 14 degrees, it's a pretty sharp curve.
The result? One of America's most challenging sections of railroad, the Cantera Loop. Not only is the curve very tight, this is the steepest climb in California's railroad system and demanded extra locomotives to overcome gravity. These were housed in a rail yard 5 miles south of the loop, in the small town of Dunsmuir that had sprung up with the arrival of the railroad. But as local resident Louis Dewey explains, there was more to Dunsmuir than just a railroad siding.
One of the main reasons it was originally popular with tourists is because the train stopped here. And Dunsmuir is the hub of what used to be a blue ribbon trout stream.
In fact, the official city slogan is, "Home to the best water on earth."
For more than 100 years, Dunsmuir was one of California's best-kept secrets. But one night in the early 90s, the town became famous for all the wrong reasons. On July 14, 1991, a 6,000-foot-long freight train was traveling up the West Coast from the San Francisco Bay Area to Portland.
The train was headed north up the twisting Sacramento River Canyon, and about 9:40, they were approaching Cantera Loop. The train had 97 cars, 11 loads, 86 empties, and 4,294 tons.
Thousands of trains go through the Cantera Loop every year. But this time, something went disastrously wrong. The lead locomotive and 7 cars derailed and fell into the Sacramento River.
It's a 14-degree curve.
Railroad engineer Gary Mahan was one of the first at the scene.
As I pulled up here, there was the engine laying on its side, and I observed numerous cars in the river. It was dark. I noticed the tank car partially in the river, but I had no idea what was in it.
What was in the car was 19,000 gallons of a highly toxic herbicide. Although no one knew it yet, this would become the worst environmental disaster in California's history. July 14th, 1991. A freight train derailed on California's Cantera Loop, spilling thousands of gallons of the herbicide metam-sodium into the Sacramento River. Attorney Donald R. Bitblett later worked on the case.
Metam-sodium is classified as a biocide, which means it kills any living thing. When it mixes with the water and turns into a combination of hazardous substances that would go off into the atmosphere.
Few people have heard of metasodium, but it's one of the most widely used pesticides in the United States.
The so-called best water on Earth had been contaminated by this toxic train load. Hardware store owner Ron McLeod witnessed the devastation unfold.
When I looked at the river, it was kind of a greenish brown color rather than the clear water that we typically see. And I could see fish floating in the river, belly up, and it was an indication of what had happened.
Almost every living organism between the Loop and Lake Shasta, 40 miles or 60 kilometers away, was poisoned. The river was so polluted, it was nearly 3 days before scientists were even allowed near the water.
In the coming days, more than 1 million fish died.
The river was closed, of course, immediately. People that had been coming up for 20 or 30 years as a family didn't come up the next year. And they didn't come up because, of course, they couldn't go do their fishing.
Luckily, no one was hurt, but this was the worst environmental disaster in California history, and a catastrophe for Dunsmuir. But thousands of trains had navigated the Cantera Loop for years, so questions were asked. Why did this one come off the rails so spectacularly? An official report concluded that the derailment was, in part, caused by the configuration of the 97-car train, with too many empty and light cars at the front. When it took the steep uphill curve, the rear of the train pulled back, causing a phenomenon known as stringlining.
Imagine this string is the train going round the curve. So long as the forces are balanced, it stays curved. But if the heavy weight at the back pulls against the front, then there's a giant tug of war, and bang, the lighter trains in between are pulled off the track. That's why it's called stringlining.
With the imbalance in the load, the train was primed to derail, and bad luck made sure that it did.
Here's a simulated train approaching the Cantera Loop. This is the car of the chemical metam sodium, an agricultural chemical. And the train was heading for the loop, and a curve oiler caught one of the locomotive wheels, and it slipped, then dumping the car of metasodium in the river.
Railroad engineer Gary Mahan thinks that, as well as the weight distribution, a fault in the lead locomotive might have tipped things over the edge.
It was reported that the engine that was derailed and laying on its side had not been working properly. It was surging, which meant it was jerking the train. And unfortunately, it did that just as they started around this curve. If that engine surged and there was enough power up there to stringline the cars off the track, had it been running right, maybe the derailment would not have happened.
The restoration and cleanup led to the largest environmental settlement in state history. To keep it from ever happening again, a barrier was built to prevent cars from being stringlined into the river, and new regulations on train configuration were implemented.
Following the investigation, the Union Pacific limited the length of trains traveling along the canyon, reduced their speed, and upgraded the locomotives pulling the train.
Finally, action was taken to get the Sacramento River and Dunsmuir back on track.
The accident still ranks as the largest hazardous chemical spill in California. But thanks in part to a 3-year fishing ban, most species in the river have completely recovered.
Hopefully, lessons have been learned so something like this never happens again.